Hello, physics people. Welcome to our conservation of energy topic here. And let's go over some basic ideas real quick. So first things first, I want to cover what this idea of being a conserved quantity is, right? And so when we say something is conserved, we mean it remains constant. And so I think we're familiar with the idea of the conservation of energy. And basically what that means is all of the energy in the initial side of the system, oops, wrong color here. So all of the energy to begin with has to equal the energy at the end, or the final energy, right? And so this concept right here is going to drive everything we're going to be talking about today. Mechanical energy is all of the energy we've been talking about up until this point. Potential energy is the mgh thing, right? Kinetic energy, and then we have the potential energy of the spring. That is 1/2 kx squared. Then we have kinetic energy, 1/2 mv squared. All of this is measured in joules, right? And so when we talk about this, we have this mechanical energy idea, and all of the energy we're talking about is basically mechanical energy. And we're adding up, all forms of kinetic and all forms of potential as we work through this. So we have our example here of a little pendulum in the picture. When we look at it, there's a couple of positions we're going to look at. Here's position 1, and down at the bottom, we'll call this position 2. And one of the easiest ways to think about this is at the highest point, or position 1, we have two types of energy going on. We have potential and kinetic. Well, potential energy is going to be at its maximum value. It's going to be as high as it'll go, while the kinetic energy is at its minimum, right? As you can imagine, as the pendulum swings up, it slows down on the way up and eventually stops, right? So at the lowest side, we kind of have the opposite thing that happens. Potential energy is at a minimum, while kinetic energy is at its maximum. It's actually moving the fastest at the bottom point, right? So here, it's the fastest, and at the top, it's the slowest, right? And that kind of gives you the relationship between the kinetic energies and how fast the object is moving. So a quick example, we have someone starting from rest, sliding down a frictionless slide. And so for us, this frictionless is really important, right? It's not going to take away any work, for example. So our picture kind of looks like this. We have our slide here. And we're going to have two positions. We're going to call this position 2 and position 1, 1 at the top, 2 at the bottom. And we have the givens here, right? They start from rest. They zoom down the slide. It has an initial height of 3 meters. So my 3 meters is over here. What is the speed at the bottom of the slide? So we could do a lot of, forces and dynamics and kinematics and all that. But what's cool about this is conservation of energy kind of allows us to cheat a little bit in terms of the kinematics using a couple different principles. First thing we need to realize is that the initial energy of the system is equal to the final energy of the system. So at position 1, we understand that potential energy is at its maximum and kinetic energy should be at a minimum. And so from that at rest, that initial kinetic energy is going to end up being 0. At position 2, we realize that there's a potential energy. It is now at a minimum. And as you can imagine, as I'm sliding down the ramp, I'm gaining speed. And at the bottom, I'm moving the fastest that I will go. So using this idea of this energy initial minus energy final, we're going to add up all the forms of the mechanical energy that we've been talking about and set it equal to the final. So it looks something like this. The potential energy in the initial side plus the kinetic energy on the initial side equals the potential energy final plus kinetic energy final. And what happens is kind of interesting. There's no initial kinetic energy. At the same time, there's no final potential energy. It runs down to the bottom. So when I do that, I can throw this at it. So potential energy initial, that's mgh equals 1/2 mv, I'm going to say v sub f squared for that final velocity. Here, the masses cancel. And do a little bit of math here. I get v is equal to the square root of 2gh. So when I throw the numbers in there, I should get about 7.7 meters per second at the bottom of the ramp. Kind of cool. Example 2. So it kind of has a lot of words here, but what happens basically is the person jumps up, and we had this problem way back when we did kinematics. The person jumps up, goes up, and then comes back down with that same final velocity, right? They're just pointing different directions. Well, what happens is this person essentially jumps a distance, and they have some initial energies at the beginning and at the final, and we can use this to figure that out. So once again, we have the initial energy is equal to the final energy. So the potential energy on the initial side plus the kinetic energy on the initial side is equal to everything on the final side. So at as the person jumps, right, at the very top, the kinetic energy should be at a minimum. The potential energy will end up being at a maximum. This would be position 2, or the final side up at top. The bottom means the kinetic energy is going to be at a maximum, right? So as soon as I leave the floor, I'm going as fast as I'm going to go as I jump. And the potential energy here is at a minimum. It's actually 0. I haven't lifted off the ground yet. So on the initial side, that means potential energy on initial goes away. It's 0. The final kinetic energy goes away. It is also 0. Leaving me with my kinetic energy, so 1/2 mvi squared, right? The initial speed is equal to mgh. So notice I didn't have a mass in the problem, and typically what happens, remember, is the mass gets canceled out. We'll be able to calculate later if we needed, but for now we're just going to run it this way. Solving for the height, right, where how much did the center of gravity raise? Basically, how high did he go? Solve for h, I get vi squared over 2g. And that is the height that the person is going to go. And when you throw the numbers in there, you should get about 0.25 meters that he jumped. The last question is a very typical question when we see this. We have a person that stands on top of the diving board, so a 10-meter board, that's pretty high up there. We're given his weight, right? So it's actually the FG is 755, right? So if we wanted the mass, we'll have to divide by it, so we might have to do that here in a little bit. So we need to first find the mechanical energy of the system. So for part A, all of the mechanical energy is in the gravitational potential energy. So what that looks like, here's my diagram real quick. That's 10 meters, person sitting at the top, right? And then he's going to obviously be going down with a certain speed at different points in the path, okay? So for the first part, the total mechanical energy of the system is all gravitational potential energy. So that's the same thing as potential energy for us here. So mgh. So we throw our numbers at it. Here we realize we need the mass of the object. So if Fg is equal to mg, and I know that is 755, I'm going to divide by 9.8, and I get a mass of about 77 kilograms. So here's my 77. There's my m. Go ahead and use 9.8 for gravity, and he's 10 meters up in the air. So the total energy in this system is 7546 joules. Total energy in system. So what part B asks me to try to figure out is how fast is he moving 5 meters above the water surface? So it's really tempting to just divide it by 2 and then figure that out, but that's not quite how it works. So the total energy in the system is going to equal the energy due to the kinetic energy he's falling plus where he is potential energy-wise. He's halfway down there, right? So I know what the total energy of the system is, right? That is 7546 joules. Well, for the kinetic energy side, he is at 1/2 mv squared. I don't know what that v is, but he's moving at some point, especially if he's halfway down. For the potential energy side, I know everything about the potential energy side. That's mgh. So when I plug these numbers in, 7546 days, so 1/2 the mass of the guy was 77. There's my v squared. And notice I know everything about the potential energy side here. So I got to do a little math here and solve for this v squared. So I'll leave that to you guys. But velocity, you should get about 10 or 9.9 meters per second squared, or I'm sorry, just meters per second, and he's going in the down direction, of course. He's going down. And that's pretty much it. So the key to understanding these is looking at this and knowing that the total energy of the system is constant, that all of the mechanical energy pieces here we have the kinetic energy and the potential energy, those things add up to some total amount. So that's going to be key to figuring out how to do these kinds of questions. All right, let me know if you have any questions. We'll discuss a little bit more in depth in class. All right, thanks. Bye.